Hello everyone, this is Zhiyun from Tsinghua University. It's my pleasure to introduce Unicorn to you. Unicorn is a coverage-guided time series databases parser. Parsing is an automated software testing technique which generates random data as program inputs. It has been applied to traditional relation databases for decades and discovered many bugs. However, because of the unique attributes of time series databases, existing parsers are hard to directly adapt to time series databases. There are two major challenges due to the characteristic of time series databases. The first major characteristic is employing time series state. As we all know, traditional relation databases store and fetch data in relation model. Table-based storage models are designed for the complex calculate and query. Different from traditional relation databases, time series databases are designed for the IoT devices, which usually generate time series data. Time series data represents a collection of data values observed from a sequential measurements over time. To efficiently store and fetch time series data, new storage models are designed. For example, the LTDB storage data with tree-based storage model. As a result, the time series databases import different grammars for queries. Another critical characteristic of time series databases is handling exception implicitly. The usability and reliability are very important for time series databases because IoT devices are widely used in many critical areas. Therefore, time series databases are designed with complex distribution structures. They generally contain hundreds of components which have complex interactions with others during runtime. Any exception in these interactions should not cause the server to go down. For example, the figure illustrates the implicit exception handling in LTDB. To support different functionalities, LTDB rejects the many threads at the beginning. The time series storage thread and the time-oriented query thread and the IoT data management thread are the three main threads. If any exception happens in the one thread, the implicit exception handling mechanism will handle the exceptions to keep the server running normally. Here we present a bug causing damage to the database's integrity of LTDB. The database's integrity requires that the data storage in the server is logically consistent, correct, and valid. The left POC shows the simplified state to trigger this bug. The LTDB performs the actions as follows with the seed. Step 1. Set the TTL for the existing time series storage group. Step 2. Insert some out-of-date records, which will be automatically detected. Step 3. Flush the time content and unset the TTL. Step 4. Delete the data and reinsert some new records. Step 5. Flush the time content and query the date in the root storage group. According to the database's integrity, the server should have returned some time series records insert in step 4. However, the client just received an error message from the server. This bug can hardly be detected by existing parsers because it was triggered with minuscule symptoms. Traditional parsers detect bugs whether an input runs normally without triggering any crash of the server. However, this bug doesn't crash the server directly. Even the client continues to run normally after receiving the error message. It would be missed by the detector of the existing parsers. Luckily, after analyzing this bug, we found that unruntime exceptions was ruined from the optimizer of the server, like this. To overcome the challenges, we designed Unicorn. It contains two parts, namely hybrid input synthesis and the proactive exception detection. Hybrid input synthesis first constructs the hybrid specification with the traditional circle specification and time-oriented models. The figure shows the create statement for the QuestDB LTDB TD engine. It can be generated with two paths: the general skeleton and the time-oriented model. The general skeleton is from Postgres specification. The time-oriented model is defined with the features of time series databases. For example, the create statement of timescale DB can be constructed by adding a time series element to the general skeleton of Postgres SQL as an attribute. Then, the IoT query generator generates time series query by mutating seeds based on the hybrid specification. The query which has new behaviors will be preserved to the seed pool for further mutation. With the hybrid input specification, Unicode mutates queries by changing the structure and the data which has time series features. The algorithm illustrates the process of time series mutation. Unicode first translates the original seed into the AST for better understanding and analysis. Then Unicode identifies the time series state nodes and time series structure of the abstract syntax tree based on the specification and mutate new queries by changing the data nodes or structure nodes. For example, the query select statement is firstly translated into the AST like this. Secondly, Unicode identifies the time series data node and time series structure node. Specifically, the prefix pans, the function node, and the LB black nodes are belong to time series data nodes, and the select elements from clause and the special clause belong to time series structure nodes. Then assume Unicode chose mutating new query by modifying the structure like delete the special clause. A new abstract syntactic tree was generated and it was finally translated into the final select statement in the rest part. Proactive exception detection uses engines to collect exceptions. Engines are managed by the anomaly detector, and they will send the exception message to the detector. Finally, the anomaly detector deduplicates and reports bugs along with their triggered input and caustic traces. Specifically, a large number of threads will be registered when the server and client starts. The context includes the error message of the thread are all shared in the same runtime environment. Therefore, we designed the engine to capture the error message from the runtime environment. One engine is used to follow one process from time series databases by instrumenting on exception handling code. Unicode first locates the exception handling code and gets all the customer exceptions in time series databases, which are used to distinguish the unchecked exceptions. Then Unicode scans each exception handler and instruments those that don't throw capture exceptions but implicitly handle it to capture an error message. For example, the right listing details the instruction code in an exception handler of LTDB. It first checks the exception type. If the exception belongs to unchecked exception or it is a serious accession, the detailed information of the exception will be recorded and sent to the engines after the execution of the seed. Based on the instrument code, engines can directly get the exception message from the runtime environment. For evaluation, we choose 6 popular and widely used open source time series databases as the targets, namely LTDB, IROSDB, QuestDB, TimescareDB, TD Engine, and GridDB. And for the performance comparison, we have also adapted the basic browse buzzers, Smith, Lancer, to those time series databases, which are widely used to test the relational databases in industry. The number of the basic blocks and the bugs are used as two basic metrics for evaluation, besides for a fair comparison. When we finish buzzing, we collect the seeds generated by each buzzer and dry run the seeds to uniform the basic block coverage. The left table shows the total number of basic blocks covered by each fuzzer, and the right table shows the number of bugs detected by each fuzzer. We can see that Unicode performs better than CircleSmith and CircleLancer both in the number of basic blocks and bugs. Specifically, in 20-hour experiment, Unicode covered 155% more basic blocks than other fuzzers-based results on average. Also, it found 14 previously unknown bugs, while other fuzzers detected 2 at most. The figure shows the growth trends of the number of basic blocks for each fuzzer over 22 hours. By comparing the curves of Unicode, CircleSmith, and CircleLancer in each sub-figure, we can see that Unicode is faster to cover basic blocks than others. To evaluate the effectiveness of hybrid input synthesis, we implement Unicode no hybrid and Unicode no random. Unicode no hybrid disables the time-oriented model and only uses the traditional circle specifications. Unicode random further disables all specifications. It is like FL that uses random mutation to generate new seeds. The right figure shows the number of basic blocks covered with 3 methods in 20 hours. It shows the importance of hybrid input synthesis for improving coverage. Compared to Unicode random, Unicode improved 32% basic block coverage on average. More importantly, we found that the time series model in hybrid input specification plays a vital role in the Unicode performance. Unicode covers 28% more basic blocks than Unicode no hybrid on average. To further illustrate the effectiveness of proactive exception handling, we implement Unicode no detection, which disables the proactive exception detection and only detects anomalies that cause crash. We collect the seeds causing the bugs from the Unicode and dry run them with Unicode no detection. The left table shows the number of the bugs found with 2 methods. The second column represents the number of the bugs found by Unicode no detection. From the table, we can see that proactive exception detection is critical in discovering bugs. Unicode no detection will wrongly consider some buggy seeds as normal. Specifically, without proactive exception detection, Unicode no detection only finds 21-hour bugs using the same seed, which is only the half of Unicode. And the right table also lists the statistics of 42 discovered bugs. Among them, 33 has been fixed by the developers. Finally, we give a conclusion. Generating semantic correct time series queries and detecting anomalies handled implicitly are 2 major challenges to test time series databases. Unicode overcame the 2 challenges with hybrid input synthesis and proactive exception detection. Finally, Unicode covered 155 more basic blocks than the best results of state-of-the-art methods on 6 time series databases. Furthermore, Unicode detected 42 unknown bugs. Thank you for your listening.